Everything okay? Great. So, first of all, I would like to thank you for this opportunity. It is an enormous pleasure to stay here today and to see many friends from Brazil and from the other parts of the world. So, thank you very much for this invitation. Thank you, Rafael, to organize this. Okay. Well, my name is Felipe Fanchini. I have been working since last year in the Einstein Hospital Israelite. I intend to talk today about quantum optimization without classical optimization. So it's a kind of algorithms that's no parameterized algorithms. And I intend to divide my presentation in three parts. Since we are just in the beginning to work with quantum computation in our hospital, I would like to introduce quite briefly what is the hospital, why it's important for us to begin to understand, to research about quantum computing. And also, I intend to explain you what's the main focus of our research. After this, I intend also to talk about a few results, not connected directly with the quantum optimization, just to demonstrate our new results. And in the middle, I will just talk about this, our last result, that is connected with quantum optimization algorithms to solve specifically Kubo problems. Okay, so the hospital is a Rouge hospital, but our research center is in the state of São Paulo. We have other units in other places, but we have a Rouge research center in the capital. We have more than 1,000 researchers in the center. It's a university also. And if you have a look in the numbers of our research center in the hospital, you see that you have more than 25 collaborators, 13,000 doctors, 1,000 research projects, and you have been working with high performance computing, and this is why it makes sense for us to introduce quantum computing in our center. We intend to understand how quantum computing can, in some way, in the future, we know about it, that we are talking about medium term, long term, but we need to begin to explore this. So this is the idea of our research center. Okay, just to talk a little bit about, okay, it's important to emphasize that we are the 16th hospital in the world, the best hospital in the world. So we reached this mark this year. So it's a Rouge center. Okay, so of course that we are talking about an interdisciplinary approach involving quantum computer, medicine, data science, and it's important to emphasize that our focus is in ethics and equity. Equity is quite important for us, okay? This is quite important for me to emphasize. So we intend to apply this advanced science to resolve problems for, to reduce inequalities, to improve in diagnosis. Of course, that we intend to develop talents in our hospital, and we believe that's quite important for Brazil to have a strategic position. Okay, just to emphasize our mission. So, as I said, we have a high performance computing center. So we intend to integrate quantum computing, AI, machine learning to develop some innovative solutions. The general objective is, of course, to enhance diagnosis, therapies, to expand accessibility, and also to position Brazil in global forefront of health technology. And again, our focus is in equity, applications that primarily benefit vulnerable populations, and of course that we are looking for equity to addressing historic neglect health problems. This is our main mission in the hospital. Where we will use quantum computing or classical computing, machine learning, artificial intelligence. So We divide it in three main aspects: genomics and clinical research, diagnostics, treatments, and interventions. So the idea is to apply classical computation, quantum computation, to try to solve these kinds of problems. We know a lot about machine learning. We have more than 100 researchers working with machine learning, artificial intelligence, and now we are trying to connect some new aspects in our research, introducing quantum computing. So, before to talk my main results, I just want to introduce some of our recent research, just to exemplify why it's important for the hospital to introduce an area of quantum computing in our center. Okay, so the first manuscript that I want to share with you is this to DNA assembly. We use a Falcon algorithm. Falcon is the algorithm that I will talk here today. This is a feedback-based quantum optimization algorithm. They don't have classical optimization, it works. And the idea here, just to illustrate, is to take strips of DNA and try to connect and to join all of them together. When you read a DNA strip, you read in parts, and in the end, you need to connect all of them to construct your full DNA. So we can solve this just translating this in a trivial salesman problem. And once we do it, we can solve with a quantum optimization algorithm. I will not take the details, technical details. I will see if you would like to have a look. Of course, that I'm open to discuss with you. Other paper that you have been working is using distillable knowledge. What's the problem here? There is many foundational models that are very powerful, but they are very heavy. So the idea here is to try to use these foundation models to teach other small models, since that they work as students. Of course, they don't have the same precision of the big model, but the idea is to try to reduce the number of parameters. For example, to put this algorithm in a smartwatch, for example. It's quite difficult to introduce a rude model in a small device. So here, what we do is take the state-of-the-art foundation model for ECG, and you use this model that has 10 million ECG recordings. They can detect around 50 disease categories. They has 22 millions of parameters. It's too heavy to introduce in a unit care, intensive care unit, for example, or even the smart marsh. So we need to train, we try to train other models with less parameters to see if we can take some similar results. So this is the main idea, a teacher model, very rude. We try in some way to transfer this knowledge for a student that's small. We did it to train a residual network, a CNN, and also a variational quantum circuit. And as you can see, we can train a student, a VXC, with less parameters than the others. But of course, that you need to pay attention to the results, the metrics. So the original has more than 76 million parameters in the end, and our student has 25,000. And if you compare the metrics, you see that the VXC can in fact learn better than the other ones, even with less parameters. This is important to emphasize that you are just working with a VXC with 6 qubits. So I prefer to talk with this as a quantum-inspired algorithm. So we can implement this in a classical computer. We just use the ideas that comes from the quantum mechanics, and then we use it to create a classical algorithm that works better than the others, the classical ones, with less parameters. So this is also other area of research that we are looking and we are researching. Finally, the last result that I intend to talk is the generative adversarial networks to create breast ultrasound images. This is quite important for us because when you are working with data, medical data, they are quite unbalanced. So it's quite difficult to implement a machine learning, artificial intelligence when you have an unbalanced data set. So you can create synthetic data using generative adversarial networks or diffusion models also that we have working. And the idea is to create synthetic data to balance the data set and then to obtain better results for classification. So here we just create data sets with two quantum algorithms, quantum-inspired algorithms as well. It is running in a classical computer, it's a simulation. But as you can see, the mosaic, that's a quantum version of a GAN. You can reach better AUC, better metrics, when you create synthetic data with them. So this is just to explain why we are looking for quantum computing and how we can introduce quantum computing in our research in the hospital. Okay, so far so good. Now, just in focusing on the results of our main title, I need to talk a little bit about the quadratic and constrained binary optimizations. This is the kind of problems that we intend to solve using a quantum computer. And the idea is to use these kind of problems to be naturally applied in our process. So we can use it for hospital logistics optimization. We can use these optimization algorithms for genomic pattern analysis, medical image segmentation. You can also use this. For drug discovery, it's a bit different because you use the same sets of algorithms, but it's not general a kubu, but you can use the same kinds of algorithms as well to discover new drugs, and also to radiotherapy planning and many, many other aspects. So to solve this problem, since it's important for not just for our company, but for the industry in general, we have been working with an algorithm that's called Falcon. So it was published in 2022 by Alicia Magan and the co-authors. And the idea here is to try to find the optimal solution. And just to explain, the idea is mainly calculate the ground state of Hamiltonian. This is the point. And this algorithm, there is no parameter optimization. So it's not a hybrid algorithm, it's full quantum. You can do it without a classical optimization algorithm. And the idea is quite simple. It's based in the Lyapunov optimal control. So basically what they did is they trotterized this optimal control strategy. And then they developed this feedback where the next parameter of the second step is calculated in the first step. And then in the following, the third, I implement in the fourth, and then by means of feedback, by means of measurements, I can estimate the other parameters of the circuit. So I don't need a classical optimization. It's interesting because, in general, this classical optimization, when you work with Ikawa, VKE, is quite difficult as well. You change a problem, a difficult problem for another difficult problem. But with this kind of strategy, we can have some hope that we can find the ground state without a hybrid algorithm. But there's a problem, of course. I will show you. So we began to study this, to study quantum phase transition. I was not in the hospital at that time, so but you have been working with this algorithm as well. And the point is that if to implement this algorithm, here's the algorithm, the model that we studied in this paper. But the problem is that we need too many layers. You see, 600 layers to reach the ground state. So okay, it works, but certainly it's not for fault-tolerant. It's not for NISQ devices. You need a fault-tolerant quantum computer. So what we did in the last years is to try to make this algorithm better. Is it possible to improve this algorithm? And the answer, yes, we can improve it. In the last months, in my point of view, we reach a really good result where we can find similar results with just 5 layers or 6 layers. It's really good. But of course, that's more to study to see what we can do in fact. So this is our first strategy, to try to find a better version of the Falcon algorithm. So here we discover a strategy with our colleague Bernardo, and he have been working with time rescaling, and the idea is to change the Hamiltonian by, as the name said, rescaling the time. So you need to find a function that satisfies some bounding conditions, but once you do it, you can just change a little bit the algorithm. You see that there is extra parameters, but nothing changed, just these parameters. We have some extra terms that you can introduce to accelerate this process. And in fact, it works quite well. It not solve our problem, but if you compare the original Falcon with the time regularization, you see that you can reach a success probability faster than with the original version. Here we try to solve a max cut problem. It's a quite common problem in the machine learning. The idea is to separate a graph in 2 parts, and we need to cut the maximum as possible. And as you can see, we can reach a really good result when we introduce this time regularization. So it's good, but it's far to be enough, because even 500 layers, 200 layers is too much for today. So in this sense, we are looking to a new strategy. And in that we find really good that what I want to talk to you. So, okay. So this is our last manuscript on this research area. So we introduce a measurement guide state refinement. It's like a measurement guide initialization. How it works? I will try to explain it quite easily. So when you run a code in a quantum computer, in general, if you have a lot of noise, you will reach some histogram like this. This is each bar is base states, base elements of the space. And as we can see, there's some of them that are higher than the others. So what we did is the following. We just run our Falcon for very, very shallow circuit, like 5 layers. And once we do this, we just separate some of the results, the best results. How many? It's a parameter. You need to choose 5, 7, 8, 10, I don't know. You need to try and test. But once you separate it, you can use this tip to initialize your circuit again. And then you repeat the process with quite shallow circuits. So this is the circuit. So the idea is to run Falcon for very small diff, like 5 layers. Once we obtain the results, we select a number of the strings that's more present. Once we calculate it, we calculate the marginals, the probability, we look for the first qubit, we count how many ones, how many zeros, and then we begin the first qubit in a superposition that obey these probabilities from 0 and 1. And then we run again. Just 5 layers, repeat the process, run again, repeat the process, run again. It's important to emphasize that the answer for this optimization problem is like a string. We're not talking about superpositions. No, it's just a base element. So it works because in this case, it's clear that the answer is just a unique string. So if you compare this algorithm with the others, this is the usual standard Falcon. So you see that you need to increase the depth of the circuit because this is how it works. But in our case, we just change a little bit. Since we run shallow Falcon circuits, implement our filter, calculate the marginal estimation, and then begin the circuit again, but with a different initial condition, and we repeat the process many, many times. So we work with 5 layers, but we need to run the code many, many times. And here is the result. So if you compare, both of them reach the ground state, or at least it's near from the ground state. In the MGI Falcon is better. And if you use the usual Falcon, to reach the same results, you need 400 layers. And you can reach the same result just with 5 layers. We just run 5 layers many, many times. And then in the end, you see that energy is just going down and down, and you can reach the response. This is for, again, from a max cut. It's 12 nodes, but we can reproduce this as well for other max cut problems. So here is an analysis as a function of n. N is the number of strings that I selected. It's my filter. And L is the layers on the X. So you see there's a lot of positions that you have really good results. Of course, that depends. If you choose in a wrong position, then you will not find the right answer. But if you compare the original Falcon, in this case, you need 200 layers. Here we are talking about 2 layers. So it's quite easy, quite simple. And there is also other variants. We can just, in the beginning, to filter third strings, but when you continue to implement, then you reduce the number of strings, so you can do it this, you can then change these strategies as well. So this is what we do to solve the optimization problem for Kubo problems, okay? If you extend it for higher system, it works as well for 12 vertices, 20 vertices. If you compare with the original Falcon, you see 1,000 layers to reach results worse than ours that we reach with 50 layers. So as you can see, the method can be a solution, or at least a hope to obtain solutions for Kubo problems using quantum computers. So just to conclude, Falcon family removes the classical iterative optimizer loop. Variants like TR Falcon, time regularized Falcon, and the MGI Falcon improve convergence and success probability under that constraints. We show our results in a weighted max cut, which indicates that the energy decrease and we obtain success probability. And this shallow advantage have the potential, at least the potential, to translate directly into practical applications in the healthcare field. So my last message, just to finalize, so the true impact of the quantum revolution will not be measured by the computational bottlenecks we made, but by the barriers to access with dismantle. We must transform this unprecedented power into an engine for equity, ensure that the most profound technology advance democratizes the future for everyone, especially the most vulnerable people. So, thank you very much.
Thank you very much for the talk. Are there any questions? David?
Yeah, but I'm not sure that we can take some quantum algorithm that can be compared with a classical algorithm at this moment. I think that there is this kind of problem is NP hard. So certainly, if you increase the size of the problem, you cannot solve it in a classical computer. And at least we can find a hope in the quantum solution. So we are looking to see at least with for huge systems, we can find a solution that are at least better than the classical ones. I don't know, I cannot guarantee that's a minimum, global minimum, but we find, and it's easy to test the answer. So in theory, you can try and check using a quantum computer as well.
Yes.
Okay, thank you for, I will talk with you soon. Great.
Yeah, up there.
Just measure the probabilities of each bit string to appear, and then you just take, I don't know, the 10 most likely bit strings and prepare superposition.
In fact, we are working on it right now. We are trying to prove that it works for a cubo, but we don't have the final answer yet. But we believe that it's possible to prove that for at least when the answer is just a unique string, you can use this but I'm not the answer right now to see the proof that it works and why it works. But it makes sense because the idea is that your algorithm are trying to connect in the right direction. Yes, because this is what they do. The road that they take is believed to be the right connection because Falcon just the next step they try to minimize. It's a condition. Each step they minimize energy. So once you minimize, you just see what is the way that they are taking, and then you try to condense this information for a more precise, and then you run again, and the filter just go into the right answer. But we are trying to find a mathematical proof that it works.
And do you have any ideas about the sample complexity needed at each iteration? Because I wonder if you just measure in the computational basis and filter out bit strings, and then only proceed with a subset of those bit strings, couldn't you just proceed classically and it would be cheaper?
Well, I'm not sure if I understand your question, but
we can discuss later. Maybe.
Okay, sure, we can.
Thank you.
Yeah. So maybe the last question, and then we move on.
Are the research lowering the price in the hospital?
I'm sorry?
The research are lowering the price in the hospital?
The principal, 50% of attendance in the hospital is for free. So in fact, we ask for the rich people to pay quite expensive since we can save the poor persons in our hospital.
Okay, let's thanks Felipe again.